Hello. Hello. Okay, fine. Yeah. Okay, thanks. Okay.
Hi there, Jeremy Chapman for Microsoft Mechanics, working from home. I want to share a quick.
Good morning. We are now on the second session of the second day. We have with us Professor Dr. Sargur Srihari, Distinguished Professor in the Department of Computer Science and Engineering, University of Buffalo, State University of New York, USA. Sir is also the Visiting Chair Professor at Indian Institute of Statistical Sciences, Bangalore. Sir has 400 research papers in various international journals and conferences. Thank you for accepting our invitation, sir. And over to you, sir.
Okay, thank you, Sahana. Can you hear me properly?
Yes, sir. You're audible.
I'm audible. My video is okay. All right, very
Yes.
good. Thank you. So let me just give a preamble to what I'm about to say. First of all, I should thank Sahana Devegowda, the head of the department, for inviting me to give this seminar. I've had the pleasure of visiting their organization, giving a few talks. I've enjoyed each of those visits. So thank you for allowing me to be here. Then I'll tell you a little bit about my semester during this COVID time. Maybe you can see the background. I'm sitting on the terrace of our house here, and a nice cool breeze here in Bangalore, northern Bangalore, near the Indian Institute of Science campus where I've been teaching. The course I was teaching this semester as a visiting professor was on deep learning. I was scheduled to teach it from January 1st to about mid-April or so. And then there would be the end of the semester with the final exams and so on. And I was just looking for the video feed on my screen. I don't see it, but I guess that's just fine. Due to the COVID situation, the Indian Institute of Science closed for a couple of weeks and then reopened. Reopened in the sense everything was online. So I went till about a week ago doing the teaching of this course. So it was a marathon session starting January 1st, leaving out a couple of weeks, almost 6 months. So I was looking at the number of lectures I gave. It was about 40 to 42 lectures on deep learning alone. So it's a pretty big, large topic. And I wasn't even finished with everything I had to say about the topic. So it is a vast subject. And why is it so vast? It's bigger than any of the standard classical topics one could teach an introductory machine learning course or an introductory artificial intelligence course comfortably within a semester. This one, even a semester was not enough for a deep learning course. Such is the depth and breadth of the subject. And again, why this is so is because of the large volume of research that is being pumped in. A lot of bright people are working in the field today, and some of the brightest minds, which used to be working on things like statistical physics, mathematics, and so on, many of them are attracted to this field because it allows them an opportunity to bring in their best skills, which makes the field rapidly expand. I suppose it's a bit like expansion in space or something. It's just rapidly expanding at an increasing rate. Just keeping up with all the material is a challenge, and learning it is exciting. So I hope to convey that sense to you, and within the short span of 1 hour. I think we've been allotted about an hour and a half. I will cover it within a short span about an hour, and then leave the remaining time for you to ask questions on whatever topic you want within this field of deep learning and its relationship to artificial intelligence. So that's how I will cover it. Now, the material over this 42 weeks can be divided into basically two parts. One is practical methodology of deep learning. So what is it you need to know about deep learning to go and implement something? So it's practical methodology. You're not necessarily contributing to newer methods. And the other half is about research in deep learning. So the first part is largely for undergraduates to say, okay, so what are all the techniques, what kind of problems can we solve, and what do I need to learn to do that? The second one is about how can I contribute to this exciting field. A lot of the topics are in great flux and a lot of research is being done. So I would highly recommend that you also be interested in the research aspect of it. And so it's a combination of the two. So we're going to do some justice to each of these. So what I plan to do is first we'll talk about a little bit of broad AI, artificial intelligence. Of course, we are all familiar with artificial intelligence, so I won't belabor the point too much. And then what is the deep learning approach to artificial intelligence? It's one approach as opposed to the, programming approach. It's like the learning approach, the machine learning approach, the deep learning approach to the problem. And then talk about, is there a definition for deep learning? What is meant by depth? So we'll try and approach that topic about definition of deep learning. Then what are all the kinds of mathematical abilities and tools that one needs to be working in this field? And my statement here is that learning deep learning is somewhat different from learning some other topic, let's say in computer science, say networking or databases or whatever be the topic, security and so on. Here, there is essential intertwining of the methods with the mathematics and theory underlying it. And I will argue that the kind of mathematics that one needs to be familiar with it, even if you are going to be a superficial implementer, is to have a sense for the mathematics such as calculus, which has differential calculus and integral calculus, and what are all the subtopics within that. And then there is a whole reliance on probability theory and statistics, which includes sampling and variational methods and so on, quite sophisticated ideas. You can't quite say, look, I don't want to learn any of that stuff. Can I just use it? Of course, in a lot of things, you can get libraries and you can patch them together without knowing what's underneath the box. But still, architecting it, you'll need a sense for what's going on here. What does it mean when you're using a certain method of optimization, certain method of regularization? Even though it's a box, you need to have a sense for what that is doing. So we need calculus, we need probability theory and statistics, and after that we also need a sense for optimization, minima, maxima, variational methods, variational calculus, where you're not doing maxima and minima of a function, but you're working in variational space, the variational calculus, where we choose the best possible function among all possible functions. So that's an interesting topic, one level higher than ordinary maxima and minima. So that is an essential part, because you talk about variational methods of inference. And after that, we need to be very familiar with computational complexity, because why are we doing this versus that? What do we mean? What do we mean by NP complete? What is meant by sharp P complete? So those are essential things, because certain calculations, certain even simple calculations, what's the probability of my, turning right or left of the car when we have an autonomous vehicle? That again becomes a probability. To calculate that, you have to do inference, and that inference can be sharply complete, which is exponentially impossible. So what are the approximate methods to doing that? And then finally, what are the various library packages? What are all these things such as TensorFlow and PyTorch, which are used for implementing deep learning? So one has to have a sense for all of these topics. So I'll indicate what those are in a little bit more detail. Then I think today's topic is not just about practical methodology, but it's also about research. So I will talk about what I think are three areas which are very interesting in deep learning, and I will indicate what those three topics are, just to give you a heads up on that. One of them is called capsule networks. The other one is called self-supervised learning. And the final topic is probabilistic knowledge graphs. All of them are interesting topics. So I'll kind of indicate those. Those are not the only research topics one could be working on, but they seem like really interesting things to work on. Okay, at this point, I'm going to share my my slides here, and let me see if I can do this. Okay. All right, let me just ask for some feedback. I'm not seeing any of the pictures of any of the other participants here on the screen. I don't see my picture either.
Yes, sir. We are participants. You cannot see, sir, but the slides are visible.
Slides are visible. Okay, fine. So this is my basic set of slides, learning deep learning. It was largely set up as, what do you need to learn deep learning, right? That's what it was about. I added today a few slides about research topics. That goes beyond learning deep learning. You're making a contribution. You're creating deep learning. So there is learning deep learning and there is creating deep learning. One is about picking up the basics. The other one is about making a contribution to advance the field as such. So I'll cover both of those things today. All right, so the topics, again, I already gave you an overview. I feel in teaching, it's also worthwhile to repeat things in case you missed it the first time around. So these are the things I'm going to again talk about. I have a slide about what is artificial intelligence. I have a slide about what is deep learning. And then what are the underpinnings of deep learning? Okay, there is an issue of the three main pillars that are the underpinnings of deep learning. Which is neurobiology is one of them, and statistical physics is a second one, and distributed computing is a third one. These, I think, are the underpinnings of deep learning. And then the methods of deep learning, I already mentioned this. Again, let me repeat it, is calculus, both differential and integral calculus. I mean, we don't really deal with differential equations as such. I'm talking about derivatives and Jacobians and Hessians and so on. And then linear algebra, where we discuss scalars, vectors, matrices, and then multidimensional tensors. And then probability, where we talk about probability distributions, the sum rule of probability, the product rule of probability, which are used for marginalization and so on. And computational complexity, I already mentioned this about sharply complete. And then frameworks, these are the computational frameworks or typically Python libraries that are used to implement these things. The last but one topic here is disruptions in computer science and in software development. This is a broad statement that I got a sense of it from the AI lead at Tesla. His name is Andrew Karpathy. He said that he has two types of software in his lab. One type of software is written by human beings. The other type of software is automatically generated by machine learning programs which are shown lots of examples, and they learn all the parameters. And once the training is done, it has learned it. So the program you're going to be using is this machine learning, the one that has already learned, right? The trained program is used. And there the code is all a bunch of numbers, all the parameters and the weights of the network, which is not readable by any human being, unlike the human written code, which is presumably readable by a human being. And how there are two types of code, and actually the code that is written by human beings can largely be replaced by machine learned code. So the disruption is that the coding is going to be done more and more by machine learning rather than human beings writing the code, which can be difficult to deal with in terms of debugging and dealing with the tangled web of code and all that. So, which disrupts the nature of software and the nature of software development, and the kinds of things people have to learn might have to change from learning all the syntax of programming languages to learning how to curate the data for machine learning, so on. And then the last bullet point here is research directions in deep learning, which is about 3 topics I just mentioned. All right, let's move on. So this is my one slide about AI. I think we all have a sense that we are all using AI every day. When we do a search or a Google search, there is quite a bit of intelligence that is going in terms of what you're looking for, in terms of the keywords you're using, and it is trying to interpret the language that you're typing in and try to find you the most relevant information. So that is one type of intelligence that's already being used in Google searches. I also show here Baidu search, which is the Chinese search engine, which one of my former students went back to China and founded that company. So anyway, those are all search engines. My second bullet point here is understanding speech. Many of us are quite familiar with Siri and Alexa, where we speak into it. Also based on speech recognition, speech understanding, also an AI task. And the third bullet point is autonomous vehicles, which is more state of the art, which is cars that can drive themselves on highways by detecting the barriers and the lane separators and so on by using various detectors, sonar, LIDAR, video, and so on, and maps all these signals into outputs. So it's taking the images as input and produce as output the control signals for the brake, the accelerator, the steering wheel, and so on would all be controlled. So this would be a kind of a supervised learning task where we drive a car around and show it how we drive under different conditions of the road and the changing of the road conditions and so on. And so it learns from those examples to perform. So these are all examples of AI. So there is AI in almost every software we use today. So let's not belabor the point. AI is there. AI is ubiquitous. So what is needed for that AI that is underlying all those programs? I think we can all understand that there is some knowledge built into these programs. Knowledge is the car should turn itself to the right when the road is going right, or turn itself left when the road is going left. Or when you say something which is not very clear to Siri or Alexa, it is able to figure out what it is that you meant, see what I mean, or hear what I mean rather than hear what I say, right? So that is, but knowledge is needed to do that. And so how do you get all that knowledge into the program, into the box that is interacting with you? The first approach to it was called knowledge-based AI. Knowledge-based AI was to hard-code knowledge and saying it's all a bunch of if-then-else type of code that we would have to put into the program, saying if road is turning right, steering wheel should go right, right? If there is a stop sign, then the brake should press down and halt. Like that, we would have knowledge of such sort. So initial approaches were all hand-designed programs, And the programmer had to have a deep knowledge of the problem domain. What is it you're working with? Let's take the very simple example of handwritten digit recognition. Um, Handwritten digit recognition is sometimes referred to as the fruit fly of AI. That you start out many AI projects by saying, okay, let's see if we can solve the problem of recognizing handwritten digits. And there's a lot of ambiguity in handwritten digits. The zero may not be touching at the top. It's open, and while you're expecting a zero to be closed, it's open, but it's only slightly open, and so on. And there are exceptions to every description of any handwritten digit you can think of. Is a nine contain a closed loop, or can it be slightly open? So that there are all these varieties that can happen. And writing a program to think of all these varieties of variations is a laborious and infeasible task, particularly when you want to quickly adapt AI to a new task. And there are, so many different applications one can think of. And some of these early applications of AI did have human beings do the feature engineering, figure out what exactly it takes to do the problem, solve the problem. So it can be done, but it requires a tremendous amount of effort, years of effort by specialized programmers. So knowledge is needed for AI, but doing it by a hand design program is not feasible. So the solution to this problem was to learn a mapping to a representation from the raw input. So from the raw input, maybe it's the image or of an image of a handwritten digit, is to learn a representation and then go from that representation to the output, rather than go directly from the input to the output. So this is you can think of it as feature extraction. People used to write programs to do feature extraction, but even that required a lot of feature engineering on the part of the programmer. So the approach of representation learning is to automatically learn the representation. If you're trying to do a handwritten digit recognition, can you find some intermediate representation that makes the final task of figuring out its 0 through 9 much easier than having to deal with a high dimensional input of the image space, which can become a high dimensional feature vector, in which case the number of parameters you need for standard classification becomes large and the amount of data required becomes large. Whereas if you can learn a representation which is much smaller, basically a feature set, but it's done automatically, the final task of classification becomes simple. So allows AI systems to rapidly adapt to new tasks, and designing features can take great human effort, can take decades for a community of researchers. So people have been working on some of these problems for a long time. They've all figured out what are the best features. Well, it's well and good, you can do that, but you cannot adapt to new tasks quickly. So this is one of my favorite slides about 3 paradigms of AI. The rule-based system on the left, which is a hand-designed program. We just saw that already. The middle one here is classic machine learning. The one I show here goes from input to hand-designed features to mapping from features to output. This is like a feature extractor is written by people and say, okay, that gives you some set of features, and then we map it from there to see what is it. Like if the handwritten digit consists of a closed region and a vertical stroke, then it's a 9, and you do the mapping from that features. A deep learning approach would be one where they use representation learning, where the input is mapped into features automatically by a program such as a convolutional neural network, and then we map from those features to the output. In deep learning, we not only have features extracted from the input, but we go from simple features to additional layers of more abstract features, and then on to mapping from features. So deep learning is about many, many layers of these things, where we go to higher and higher levels of abstraction. And that can bring in a lot of advantages when you have deep learning, that you can, for instance, when the number of features is reduced to a smaller number, the data requirements are not as high as if you have a large number of features, as in a raw input would be. So that's one advantage, and many other advantages as we go along. So let's now define what is meant by deep learning. Can you give a short one-sentence definition of deep learning? That's what this slide tries to do. So we are saying here, deep learning is constructing neural networks that are inspired by neural networks of the brain. So we are constantly thinking about how does the brain do it? And we don't necessarily model everything that the brain does, but we get inspired by it, saying this is basically the architecture, and such as consisting of neurons, and the neurons interconnected to each other. And if there is enough of weightage of neurons firing, then the next neuron will fire itself. And there's some weightage on the connection or the synapse from that network. So basically that is the architecture, where all the knowledge is not concentrated in one list or anything like that. It's kind of spread around all these basic neurons, which are very, very simple mechanisms. A neuron is a simple device that takes a bunch of inputs and adds them up with certain weights associated with each of these inputs. And if that total sum of these weighted inputs exceeds a threshold, it fires, otherwise it does not fire. And then it connects off to the next networks it is connected to, and so on. So there are connections in it, there are weights in it, and that is how a brain works, basically. That's what McCulloch and Pitts, when they were studying the brain, showed that's how the brain seems to be working. So we're inspired by that, but there are many, many other inspirations that go on when we come up with algorithms. How do we train an algorithm to learn a probability distribution? Such as I show it a lot of examples of zeros through nines, and we needed to construct it a probability distribution spread over these handwritten digits. Maybe it's going to be a multimodal distribution with the 10 peaks corresponding to 0 to 9. Then how does it learn these distributions? So it can do inference, such as when I give you something, it says, oh, that's most likely a 7. So that involves inference using this. And it turns out the standard network design, which is actually what's called as an undirected graphical model, turns out to be computationally intractable. And that has to be done using some kind of approximate algorithms, such as contrastive divergence and so on. And then it turns out the contrastive divergence algorithm is somewhat similar to what the brain might be doing in sleeping and waking states. So this contrastive divergence algorithm generates samples from the data set. All right, we've been presented the data set. It says, okay, here are all examples of the world, real world. And then there's a model of the world constructed in the brain on the neural network. The model can be used to also generate samples. And it might not be very nice samples because it doesn't have such a good sense for what is the world like. So we kind of contrast each of these data sets, one coming from the real data set, one coming from the model of the brain. In a way, this is like the wake sleep of the human. So when we are awake, we are aware of the real world and what's happening around us. Okay, we go to sleep. Maybe the brain is also playing out some dreams, and it is also playing out what the world is like. And it also maybe looks as realistic as possible to the human being. And so, but then you can also say, well, what are some samples from your brain, because you have a certain model of the world. And then we say, well, let's take a look at the samples from the model, which is now the brain. And then there's a real world, and say, okay, what are the differences here? And say we resolve that statistically, and then go and fix the model, saying make it more realistic. So there is neural network inspiration not only at the neuron level, but also at a higher level in terms of cognitive type of behavior and so on. So anyway, my one sentence there was neural networks are inspired by neural networks of the brain. Second one is the deep learning algorithms discover rich and useful representations. So they map from the real world to some representation. Actually, in this deep learning, it goes from that representation to another representation, to get another representation like that. And along the way, it finds what is a good representation that makes the final task, which usually we refer to it as a fully connected network or an FCN, as simple as possible. The final task turns out to be what's called as a linear classifier. A simple classifier can do the job because all the hard work of learning the representation has all been done. And that representation can be like all the data lie on a manifold, lie on a surface, lie on a torus. There are some pictures shown here. The data, the real data lies on some surface. Like if you're showing all pictures of cats to the program, cats don't occupy a full range of all possible values of the features, and it is some subset of the learned representation. They all lie only here. If you move along this surface of which might be like a pancake here, you move from one point to the other, you get a different cat. You get a different cat, or if it's a face, let's say a face may be a bit more complicated. Like it would all be lying on a torus like this. And as we move around the surface of the torus, we get different faces. And of course, when you come back here again, we are back to the same face. So they lie in a low-dimensional representation that is somehow discovered by the deep learning program. So that is one of the beautiful things here is deep learning discovers rich and useful representations. Useful in the sense, well, what is it you're trying to do? And you're trying to recognize something. So let's say for that task, what is the suitable representation? And the third sentence about what is deep learning is deep learning is deep. What does that mean? It means the function. You can think of any task that a neural network does as one of learning a function to map from input to output. And the particular type of function we are learning here is a composition. In the sense, it's a sequence of functions. The input is presented to a network. It computes a function, right? It could be a function, a vector. A function's output could be a vector. So that function output is again fed to another function, fed to another function. So we can think of it as f1 of f2 of f3 of x, where x is the input. And F3 is the first one, F2 is the second one, F1 is the first one. So we say this is a network with 3 layers of depth. And so this is a kind of composition, that's what it is. And the diagram here shows that in the form of a convolutional neural network, the input is processed through layers and layers and layers. You can think of every one of these layers as a functional mapping. Of course, it's the vectors that are coming out each time, or a tensor that is coming out each time. A tensor is just a generalization of a vector and an array into a multidimensional object. And so those are the 3 things about a deep learning network. It's a neural network, it learns representations, and it's deep. That is the definition of deep learning. And another thing we can say about deep learning is that the phrase deep learning is aspirational. In that deep learning is a goal and it does not say how. So it says very broadly, when we said inspired by neural networks, learning useful representations, and it is deep. That is a very, very broad definition. And it does not really say how. There are lots of details here. Adding priors to learn high-level representation is an example. In that sense, deep learning is aspirational, like saying artificial intelligence. Okay, what is artificial intelligence? And that is again aspirational. It doesn't say how exactly artificial intelligence is created. It is like saying making the program do things which when done by human beings, we would call it as intelligent. It's a very broad definition. Also, machine learning is to learn from examples rather than be explicitly coded. So these are all very, very broad terms. Deep learning is like that. So this slide is the underpinnings of deep learning. I have a diagram at left, which is neurobiology. Okay, there is a image I found of a real human brain. Somebody is holding it in their hands. This is what a human brain looks like. So there is neurobiology, and then there is also statistical physics. There is also distributed computing. And I put some pictures of people who made important contributions to each of these areas. Warren McCulloch and Walter Pitts, these were the ones who are very interested is how does this brain work And they're the ones who inserted probes into the brain and measured potentials and so on. And they detected that the brain consists of neurons that are all interconnected to each other. The neurons are specialized cells, and they take inputs, and their output is taken out on a particular pathway called an axon, and the axon splits into what are called dendrons and dendrites, and then the dendrites touch the axons of other neurons, and that's how they transmit information, and that's how they fire. So they wrote down saying, oh, this is how it seems to be. Basically, it is a cell that fires when the weighted inputs exceed a certain sum. Fire means the output is 1 or 0, which means this could be modeled by a sigmoid function, which is a function that goes from 0 to 1. It's a continuous function. And if the inputs don't add up, then it's at 0. If they add up, it's at 1. So the activation function takes as input so it would be a sigmoid of W transpose X plus W naught. That would be the equation of a formal neuron, a mathematical neuron. Sigma is the sigmoid function that goes from 0 to 1. So what is its input? Input is W transpose X plus W naught. What is W transpose X? X is a vector which consists of all the inputs coming in. W transpose consists of the weights of all of these. So when you say W transpose X, 2 vectors multiply with each other gives you a value. There's some bias W naught that's added on. So you have a scalar quantity. The sigmoid function takes a scalar quantity as input. And if you make a plot of what does a sigmoid function look like, it's a plot that looks like a S shape. That's where the sigmoid comes into play. And if the values are very low on the left side of the x-axis, then the output is 0. If the values are very high, then the output is 1. And in between, there is S transition. So this is what McCulloch and Pitts discovered about neurons, and that forms the basis today of neural networks and deep learning. There is a lot of statistical physics that comes to play in modern deep learning, and we can thank the work of Ludwig Boltzmann and Hosea Willard-Gibbs, who contributed to statistical physics. Boltzmann was interested in thermodynamics, and he defined things like entropy, but he also defined things like energy. And we use those kinds of models, energy models, to describe probability distributions learned by these neurons. So these neurons are not just always learning to map a image of 100 digits to an output, but they're also learning probability distributions. And this is called a generative model. And Ludwig Boltzmann's work allowed us to do that. He was working with gas and so on in a jar. Hosea Willard-Gibbs was also working in these same areas. Hosea Willard-Gibbs received his PhD in 1901 from Harvard University. He was the first person to get a PhD in engineering, and he received it for the work he did for statistical physics. So while we have Boltzmann distributions that are commonly used with a certain deep learning network called a deep Boltzmann machine and so on, Gibbs, his name is used to describe a method of statistical sampling called Gibbs sampling. It's also used to define a probability distribution in a undirected graphical model, which we refer to as a Gibbs distribution, and which is extremely useful today. And then there is this whole thing about distributed computing. We saw this diagram already about layers and layers and layers. And the people who invented all the basic mechanisms of the structure of these networks, of learning the weights using backpropagation and learning probability distributions, the three main contributors who received the Turing Award for 2019 were these three individuals: Yann LeCun, Jeffrey Hinton, and Yoshua Bengio. Yann LeCun is the one who invented the idea of convolutional neural networks, how we go from layer to layer by convolving it with a bunch of weights, the kernel function. And Jeffrey Hinton invented the idea of backpropagation. how do you get this network to go from a picture of a cat to saying that's a cat and not a dog? Well, you train it by saying, let's apply a cat and see what is the output saying. If the output is saying the cat is a dog, okay, that's wrong. In which case, we take the error signal between the two and pass it backwards, fix all the weights here along the way, using chain rule of calculus to fix the derivatives of what's called as a loss function. How much is the loss? How much are wrong are you? So Geoffrey Hinton invented backpropagation, and he also invented a number of other things. So, and then Yoshua Bengio made some contributions to the generative models and so on. So anyway, those are the underpinnings. So then people ask me, can I just learn deep learning like picking up a book, saying, can I read a book called Deep Learning for Dummies? My thesis is it's not that easy. So maybe you have networking for dummies, HTML5 for dummies, coding for dummies, database for dummies, multimedia CD-ROM for dummies, beginning programmers for dummies, graphic design for dummies, maybe even AI for dummies. But machine learning for dummies, I think there is a title there also. People will sell you whatever you want. This requires a much more sophistication to get a sense for what machine learning or deep learning is doing. It's not so simple, but what does it take? Well, for one, to learn all the weights in this network, that's what deep learning is about, we would have to construct a loss function L of W. W is all the set of weights in the network, W transpose here. And the loss is, well, when you present something, you're getting something something not exactly right. So it's measured by a loss function. And you sum over all the training samples that we have, and that becomes your total loss function. And you say, well, we want to minimize this loss function over the weights. So you would have to take a derivative of the loss function with respect to W to do what's called as gradient descent. So if we have the weights W1 and W2 of the network, let's say we have thousands of weights in this network, but let's say we only had two, W1 and W2. And you can fix the weights anywhere you want, and you fix the weight anywhere you want, you get a different value for the loss function. In this case, the loss function is a function of only two weights, L, W1 and W2. So your loss may be sitting way up here. Okay, that's a pretty bad loss, the way you have picked your W1 and W2. I would like to be at a point where the loss function is really low, somewhere down here, in which case we need to make a descent along this surface here. And how do you make a descent? Which way should we go? We compute the gradient of the loss function at that point, which is what is being shown here. The inverted delta here is called nabla. So nabla W of LW is the derivative of that function, and says the first derivative. And we take a step epsilon. You move along the. This one indicates which direction is the highest change in loss. That's what the derivative tells you. And we take a step epsilon, that's a step size. You keep on moving along. Hopefully, you'll find your way to the bottom of it here. And the way we do it is we take the previous set of weight, WT plus 1 is the original values of W1 and W2. And we change, it's a new one, WT plus 1. It's from the old W2, WT, the previous setting. And then this derivative, that this equation is a famous equation called gradient descent. As you can see, this requires some heavy-duty calculus here, in that you need to be able to take the derivative of the loss function. It is not just a function with one variable. We're talking about many, many weights, not just two weights, not just three weights, not 100 weights, maybe thousands of weights or even millions of weights. So we're talking about doing calculus in very high dimensional spaces and taking derivatives of these things. And this one is only a field for the first derivative. So the methods of deep learning use calculus. What all calculus we need, we'll take a look. It uses linear algebra because we're talking about vectors multiplying and all that. That's linear algebra. And we need probability in statistics because we are talking about probability distributions. And we need computational complexity is why do we need a different algorithm? And so we need to know what is the computational complexity, and then what kind of computational frameworks or libraries and all we need. So let's I have one slide for each of these areas. So what is the role of calculus in deep learning? One of my favorite physicists is the physicist Richard Feynman. He received a Nobel Prize for physics. And there's a famous Feynman's lecture notes in physics. So at some point, Feynman said, the language God talks is calculus, right? It's not Latin or Sanskrit. The language God talks is calculus. So we need calculus not only in statistical physics to describe how the world works. We need calculus to describe how deep learning works. We already saw an example of that in terms of derivatives. So the techniques invoked here these are all the different chapters in this language of the gods. Differential calculus, we need to know about derivatives, right? Partial derivatives we need to know. We need to know the chain rule of calculus. We're talking about compositions of functions, function of a function of a function of a function. So how does the derivatives work here? Then we say dy by dx is equal to dy by dz and dz by dx as the chain rule of calculus applied many times over. We need Taylor series where we can take a function, because all of machine learning, deep learning is about learning functions. So we bring in derivatives. We are saying the value of a function at a certain point at a point x can be described by its derivative at that point, weighted by something and so on. First derivative, second derivative, so on. They all play a role in Taylor series, Maclaurin series, and so on. They constantly come up. And when we generalize from one dimension to 2 or 3 more dimensions, the first derivative matrix of partials is referred to as a Jacobian. We might even be dealing with second derivatives of the partials across variables and referred to as the Hessian. So we not only need standard calculus, we need multidimensional calculus, and we need integral calculus. Where we constantly talk about marginalization. We're saying we got all these variables, we're only interested in one. How do we marginalize all the other variables? Well, usually it involves taking some function and you integrate it over all the other variables, leaving the only one you're interested in. So that involves an integration. So you need to know something about integral calculus. And then expectations is a standard thing. So most of these networks provide you a probability distribution as output, and we are not satisfied with saying, okay, what do I do with the steering wheel? How much should I turn? If the output is a probability distribution of the direction saying most likely it is this value, but it could also be all these other values, we need to be taking a hard decision. What is the single answer? In which case, all right, take the average value, which is called expectation. Expectation, as you know, of x can be written as integral of xp of x dx is the definition of expectation, and there comes an integral to play a role. Then finally, we have optimization methods. We have to figure out maxima, minima. What is the most likely answer to this? So we need the maximum a posteriori probability, or we need to take the maximum or the minimum of the loss function. So again, we're dealing with maxima, minima. And then there is a whole important set of techniques called variational methods, where we are no longer talking about single functions. We are talking about a family of functions, and say among all possible functions, which function suits this task the best. In the sense similar to the entropy of a probability distribution is defined as integral x p of x dx. And then we ask the question, for what p of x is this maximized, this quantity entropy maximized? Then we are talking about what, among all possible distributions, which distribution has the highest entropy, and that involves choosing the right function. So it's no longer a question of maxima and minima of a function, but the maximum and minimum function, and that brings in calculus the variations or variational methods. So these are all the basic tools of calculus. At least one has to be familiar with what these things can do for you. The role of a linear algebra is we can go from a zero-dimensional tensor, which is called a scalar, to a one-dimensional tensor, which is a vector, two-dimensional tensor, which is a matrix or an array, and a three-dimensional tensor is a 3D array, and so on. And these are all organized in terms of fibers of a third-order tensor. So why do we need these multidimensional things? The objects may be images, in which case we have a two-dimensional object. The images may be color images, in which case we have 3 layers corresponding to RGB. So we now have a three-dimensional tensor, which has got a plane corresponding to R, plane corresponding to G, plane corresponding to B. Together they form the red, green, blue. So we might have a video, in which case we have a time-varying video in color, in which case we bring in a 4th dimension. So we have tensors in multiple dimensions. We may also be dealing with filters of various sizes, which creates even higher dimensions of tensors. And the role of probability statistics is plays an extremely central role in machine learning, because why do probability statistics play an important role in deep learning is, think about it, all we have is a bunch of data we are learning from. So one of the first things you can think of when you're given a lot of data, what could you do with it? You could compute some statistics out of it, saying how often does this happen, how often does that happen, and so on. That's exactly what the program is doing. It is trying to use that information to make decisions in the future. So we use Bayes' rule, which involves at least 2 variables, right? P of x given y, right? It's conditional distribution is written in terms of the joint distribution P of x comma y and the marginal distribution P of x, and there are relationships between these things expressed by the sum and product rule. The sum rule of probability says P of x can be obtained from P of x comma y by using the sum rule of probability, which says sum over all values of y and you'll have probability of x. Or the product rule, which says P of x comma y, the joint distribution of 2 variables, can be written as P of x given y times P of y, all coming from Bayes' rule. And then we have to be familiar with distributions and expectations. We have Bernoulli distributions where the values are 1 or 0, or we have multi-valued distributions, multinomial distributions, or multi-nulli. We have created our own terminology in machine learning and deep learning. Just like you have Bernoulli for a variable with 2 values. If you have multiple values, there was no proper word in mathematics for it. So computer science people have called it multi-nulli distributions. And then Gaussian and so on. Gaussian distributions play an important role. What do you mean by expected value? A huge subtopic is probabilistic graphical models. How do you represent a probability distribution using a graphical model which is directed or undirected? We create what are called as Bayesian networks or Markov networks, and we describe how to do inference with these models. Then there are what are called as Monte Carlo methods, which is if I have a distribution captured by either a probabilistic graphical model or by a table, how do I generate samples from it? We need samples to simplify the task of inference. Actually doing the full integration for marginalization sometimes is too complicated, in which case if you have a set of samples, you can average the samples and get an idea of what the probability is. And there are variation methods and so on. And what about computational complexity? If I give you a probabilistic graphical model, which has got a bunch of nodes and edges, and say the nodes correspond to variables, the edges correspond to interactions, and we have defined a probability distribution. If it is a directed model, it is by means of a simple factorization of the conditional probabilities. If it is an undirected graphical model, then it's again a type of factorization using the Gibbs distribution, where we have a product of factors and then divided by what's called as a partition function that represents the distribution. All right, so a network of some sort. There's a picture over here. Here's an undirected graphical model, which consists of a bunch of variables, which shows all the interactions. The distribution that it represents a particular distribution. It assigns a probability to every combination you can give me for all the variables. But answering a question saying, what is the probability of one combination of these variables? It is an NP-hard problem in that you have to sum over an exponential number of terms. Even if the number of variables is small, exponential means it's going to quickly go out of hand and it will be impossible to compute. So we have all kinds of algorithms for computational complexity. click trees and so on for dealing with them, or a totally different approach, which is based on Monte Carlo sampling, where we generate samples from the distribution and estimate the values from the samples. So sampling becomes an important topic in computational complexity. Deep learning frameworks are all the software libraries available for implementing these deep learning networks. This nice diagram I found a couple of years ago shows who developed what deep learning frameworks. Like we have some of the famous ones. There is TensorFlow is over here, and then Keras. These are popular, and they're Google developed products. And here we have PyTorch, which is a Facebook developed product. Microsoft and Amazon, they all had something called Gluon and so on. So just like today, there are different software frameworks for doing video conferencing, like we are doing on Microsoft Teams today. There's WebEx of Cisco, and there is Zoom and so on. Just like that, we have all these libraries available too, and so one has to make a choice of all of these. And these couple of slides are how deep learning disrupts computer science. I mentioned this in the beginning. So the software developer at present writes and maintains layers of tangled code, right? That's what a software developer does. In the future, the software developer is more focused on curating the training data, analyzing the results, and so on. So there's a change that's likely to happen here. And what about the mathematics that is needed to understand deep learning? Okay, the present computer science is largely focused on probability and discrete mathematics. Whereas in the future, I already mentioned to you what is needed for deep learning. You need probability theory, calculus, linear algebra. These are all based on continuous mathematics, right? Linear algebra and calculus are based on continuous mathematics. Probability theory is also largely based on continuous mathematics, although we do have discrete versions of them, right? And what about programming environments? C++, Java were the present ones, and the future is libraries for Python such as TensorFlow, PyTorch, Gluon, etc. And some people are predicting in 10 years most software jobs won't involve programming, because that is human written code. Just like we are saying we want to get away from humans writing code to extract features, maybe we'll get away from humans even writing the code. It's all going to be just a matter of showing examples, and it's learning how to do it. Just as if a project manager interacts with the customer saying, what would you like? And the customer says, well, for these inputs, this should be the output. Okay, sir, I'll get you the program. But the program is not written by anybody, but he just used machine learning to produce the code. And so nature of software is changing. And nature of hardware, today we still largely use GPUs. Only for the graphics we use graphics processing units, and almost all of this distributed computing will be done by GPUs, such as produced by NVIDIA and so on. I guess this is why Intel and all are slowly losing the market, because people are moving away from the conventional approaches. So, and then people argue that deep learning is not just another tool, it's a fundamental shift in how software is written. So, Andre Karpathy talked about software 1.0 and software 2.0. Software 2.0 is 1.0 is a classical stack. It's code we write in Linux, Apache, MySQL, Python, Perl, whatnot. And software 2.0 is a code written by the optimizer. The optimizer is figuring out what are all the network weights. And here is an example of the network and all the connections with all the weights in it. So all of this is pretty user unfriendly. You cannot look at any other code and say this is what it's doing. It's extremely hard to do that, because there are millions of weights involved. And there's no human involved in coming up with these things. It's all automatically generated by machine learning program. We can say, well, code generated in Karpathy's lab for Tesla, written by human beings, this is all 1.0, and this is all code generated by machine learning programs 2.0. The 1.0 is readable, but it's hard to maintain, because you need to figure out what is the logic. 2.0, well, you just need to change the training samples and so on, but you don't And you can't explain it what's going on. That's one disadvantage. That indicates an area of research. So one area of research is called explainable AI. Is all this deep learning, you generate all these things and it can't tell what it is doing. Is that good? Particularly in the medical domain, to administer a particular drug, don't you want to know why it is saying that? Simply saying administer this drug. Yeah, you need some explanation, no doubt. But today's deep learning researchers say, look, I'd rather focus on getting better deep learning solutions rather than focus on generating human learnable answers, and say that's a distraction. And at what level of understanding do you need? So it's not a well-defined problem. So explainable AI is a bit of a controversial area, whether one needs to work in that or not. More concrete areas are capsule networks, self-supervised learning, and knowledge graphs. Here is my one slide attempt at capsule networks. Capsule networks are a solution to a current problem in deep learning networks. If you give, let's say this is a Picasso's portrait of a woman, it's a painting, and it has got a large eye here and a mouth and a nose and so on. So look at this grotesque view of a face here. You give such an input to a conventional neural network, deep learning network, it will say, oh, that's a face. Because it's got all the components, the eyes and the nose and the lips and so on. And but it's not by any means a real face. And so what Jeffrey Hinton proposed for the capsule networks is that a convolutional neural network extracts features correctly in lower layers, but wrongly activates neuron layer above for face detection. So he says we are correctly detecting 0.7, 0.9, 0.9, 0.7, 0.9, every component. That's an eye with 0.9, that's an eye with 0.9. That's I don't know what, a nose with 0.7, that's a lips with 0.9. And then it says, well, putting it all together, that's a face with 0.95, it's a scalar value. So what Jeffrey Hinton says is you are allowing only one scalar value to move from one level to the next. And maybe that should all be in the form of vectors, and you can have a better description. So you are carrying along. So in this case, we are carrying along 0.7, which is the same 0.7 as over here, and then there is also 0.0 and 0.4 in terms of some location information, and 0.9 and location information, 0.9 location information. So you're passing along a vector from one layer to the next layer. In the conventional neural network, it was all single units. Now we have sets of units carrying along these values, like 3 units here. We refer to those 3 units carrying along the scalar values as capsules. And we can say the capsule nets, the neuron contains likelihood as well as properties of features. So a vector containing likelihood, orientation, etc. So he's saying carry along more information. So it seems like an intriguing idea, but it hasn't panned out a lot. Jeffrey Hinton only proposed it a couple of years ago, but it hasn't really become a very dynamic area, but it seems to make sense to want to pursue. Another topic which seems to be of a lot of current interest is called self-supervised learning. We are, machine learning folks at least are very familiar with supervised learning and unsupervised learning. In supervised learning, we have examples of input-output behavior, and say here is an image of a 7, and we tell it that's a 7. This is an image of a 5, and we tell the program that it's a 5. That's called supervised learning. So it can learn what a 5 looks like, what a 7 looks like, and so that is the nature of that. Whereas the unsupervised learning is I throw at you a whole bunch of data and ask you to figure out whatever you can from that data. So in unsupervised learning, we go about constructing a probability distribution of the data, and we say, oh, look at that, there is 10 peaks here, maybe it corresponds to 10 digits, and these are all the different classes. And we learn, like in k-means clustering or something like that. That's unsupervised learning. Then there is something called semi-supervised learning, where we say, well, I'll give you a few examples, labeled samples, but I cannot give you a whole lot of labeled samples. You need to figure that out yourself. And if your distribution of the data is multimodal peaks, and you give me a few samples corresponding to each of the peaks, then you can say, well, that peak corresponds to this class and another peak corresponds to another class, and so on. So semi-supervised learning works well when the probability distribution of the data is suitable for that. Self-supervised is yet another approach which has emerged more recently. And this, they're saying, if you're given a large unlabeled image collection, we can learn something from it. This says you can extract, for example, random pairs of patches. Let's say we have given this image of a cat, and we have two patches. It's a pair of patches, and it goes about learning to predict position of the second patch relative to the first. And we say, okay, here is the central picture of the cat's face, and then here is the cat's ear, and it knows in that particular image that cat's ear happens to be on the top left. This is the left ear. So it says, okay, I have learned without you telling me anything that a cat's ear occurs on the left of the cat's face. So this is self-supervised learning. It's learning directly from the data. And here is another example to illustrate. Here is one image, and here is a second image, and we ask the question, where is the second image with respect to the first? If you look at it closely, you will understand that this is the top front part of a city bus. Something express it is saying that, and these are windows of the city bus. Okay, this is the front where the driver sits. This looks like where the passengers sit, and to the right and somewhat below. And we say the answer is this one belongs to quadrant here, right, to the right lower quadrant. That's where it belongs. And this is again two images which look like a railway station and something like that. So this second image may be on top or something like that. So self-supervised learning is it is figuring out, and in the process of figuring this out, so what does it buy you? It makes you understand what is the nature of this image, and it's learning what a cat is on its own, saying this has got a left top ear, so there is an object like that, and so it is figuring out these objects are of that form. So there is no input. On its own, it's figuring out what is the shape of a cat, which seems like a pretty exciting thing. This is called self-supervised learning, and a lot of resources are now going into how can we have a system for learning. And one can argue again, what is the connection to the brain, human brain? Well, you see, we always take inspiration from the human brain, and we say, look, children learn these things, don't they? We don't tell them repeatedly that is a cat, that's a cat, that's a cat which is turned left, turned right. We just, sometimes we tell it that's a cat and once, and child has learned what the cat is like. Or maybe we don't even tell it that, it figures out there is something here, some animal here, figures it out. So human beings don't learn by giving lots of examples and constructing statistical distributions, but we do semi-supervised learning or self-supervised learning. So this seems like an exciting area. The third area, which is again a huge area, this is called knowledge graphs, which seems like an interesting topic, but it's already being used. Like whenever you do a Google search, you will see on the right-hand side, if you're Googling a particular object or an entity. Let's say we Googled Leonard Nimoy, who's an actor in the Star Trek movie series. if you Google search Leonard Nimoy, other than giving you the web links, on the right side it will also show you a photo of Leonard Nimoy, many different photos of him, and also some description about his movies that he has acted in, so on. It gives you all this kind of information, and one can say that all of this related information is all contained in some kind of an internal graph that Google creates. It's called a knowledge graph, Google knowledge graph. And these are called knowledge panels. So knowledge panels are information boxes that appear when you search for entities, people, places, organizations, things. And they're meant to help get a quick snapshot of information on a topic based on available content on the web. So it is not giving you just go and read this Wikipedia article about Leonard Nimoy. It's giving you a quick idea about Leonard Nimoy without having to study many documents. And Google's knowledge graph stores 18 billion facts about 570 million entities. This is a couple of years old for its search engine. So there are entities like, there's a movie, actor, and so those are all entities, and there are facts about them. That Leonard Nimoy acted in this movie, those are all facts. And the knowledge graphs provide semantically structured information interpretable by computers. So there is some kind of a graph structure going on here, and you can think of it as a graph structure like this. It says Leonard Nimoy played Spock, the character in Star Trek, and that Spock is a character in the story Star Trek. And Leonard Nimoy simply starred in, you can say, or played Star. And then Star Trek is a genre of is an example of the genre of science fiction. Star Trek is a science fiction. Star Wars is also a genre of science fiction. And in Star Wars, there was a character called Obi-Wan Kenobi. And Obi-Wan Kenobi was played by Alec Guinness. So this is just like Leonard Nimoy playing Spock. Alec Guinness played Obi-Wan Kenobi, but Alec Guinness also starred in Star Wars. So all of these connections now become a graph. Nodes represent entities, edge labels represent types of relationships, and edges represent existing relationships. And so a lack of a edge means that relationship doesn't exist. So these are the kinds of graphs, and it turns out that deep neural networks can play an important role in constructing these knowledge graphs. And basically, they extend neural language models to model entities and relationships. Neural language models are what are used when Alexa or Siri learns to understand what you said. Then a neural language model learns a distributed representation of each word and about interactions between words. So it says these are all meaningful things that go together. It's figuring out October, November, December, January, February. They might be occurring in different places, and it figures out those are all very related concepts because the way they're being used. Same idea here, that these entities, they look different, but then they are all related. It figures it out in this distributed representations. Not only it figures out the entities are related, it also figures out the relationship between entities. All have some kind of embedded vectors, just as embedded vectors in deep learning are used. So let me try and conclude now with this last slide, that deep learning is inspired by neurobiology. We don't want to forget that constantly we are thinking about how does that relate to how people do. Previous AI methods divorced from all of that, saying I'm going to write a program however I think. It has nothing to do with what the brain does. I will try and solve the problem as well as possible. So that is the knowledge-based approach. Whereas we are now talking about a neurobiology-based approach, heavy on statistical physics because of all the various distributions we work with and inference methods we work with, and heavy on distributed computing. The concept is not maintained as a singular concept, but it is maintained by distributing the value over several different nodes, and together they represent a concept. And one can show how much more efficient distributed computing is as opposed to symbolic computing. So Okay, and the methods heavily borrow from traditional science and continuous mathematics. So constantly we are talking about Gibbs distribution and entropy and Boltzmann distribution, and all coming from statistical physics and continuous mathematics, all calculus, linear algebra, probability, complexity, distributed, so on. And all of this will probably disrupt computer science and software development. I'm not saying it's going to happen in the next year, 2, 3, maybe longer than that, but slowly and surely these methods will take over more and more areas of traditional coding and so on, right? And the research topics are extremely exciting, and there is a very long range view of what can be done. One has to have the discipline to want to learn some of the tools that are needed, and I think it's going to be highly rewarding to do all of that. Okay, I'm going to stop at this point, and hopefully there is some time left for you're asking me questions. I'm happy to take on any question on any aspect of deep learning that you may have. Okay?
Yes, sir. Yes, sir. There are 4 questions that are being posted by the attendees.
Okay, I cannot see anything on my screen. If you can...
I'll just read out the question, sir.
Okay.
So the first question is, why is it conclusive that capsule nets are better than CNN? What is the limitation of pooling layers that they aren't used in capsule nets?
It's an excellent question. Jeffrey Hinton put forward this idea, and that example I showed about the distorted Picasso face and so on, it comes from his and his group's papers. And I think there is enough validation that the convolutional nets kind of become specialized. If you see what a convolutional neural network is, it is learning representations, and so on. It is saying at one level, may not be the immediate one after the raw images. At some point, it is describing discovering some high-level features. So it is maintaining that, oh, there is a mouth here now, there is a lip here now, and so on. So it is possible that these things, when you take it to the next level, are going to miss out on exactly where it was. And that information is lacking. It has only discovered that there are these features, but it is missing out. Perhaps you can engineer, I mean, there again, you might need some feature engineering going on, which we don't want, right? So we need it to work automatically. So we're saying, give it some more parameters. So one cannot argue with that. Give it a few more degrees of freedom, rather than simply saying with 0.7 probability that's a mouth, 0.9 probability that's a ear. Just tell me if it is 0.7 and where. So you need to have that type of flexibility in that. So I think that is where it comes from. It has not picked up a lot of traction. When the paper came out 2 years ago, people jumped on it immediately, say, okay, I'm going to do capsule networks. So you have to look through the literature to see what else is happening on this. Maybe you're one of those who knows how well these capsule networks work. But I like the overall motivation, saying, give it more contextual information. I'm a believer in that, saying it cannot hurt that you give it a little bit more information to carry along. And that should only help and not hinder, and rather than make your CNN very specific. All right. So I've given you a very general answer, but more information is good. Okay.
And the second question is a virtual GPU better than CPU for execution of deep learning models?
Okay. You're at the limits of my knowledge on this area. We're talking about hardware here. So, this is all today. There is all kinds of speed achieved by various processing units, and I'm hearing more and more people using NVIDIA GPUs and so on. I'm sure you could put together a virtual GPU by using conventional boards and so on. But then if you have the real thing, why work with the virtual versions? Maybe for the short term, maybe virtual GPUs may be fine, but in the long term we are looking at maybe that's what you need, because all these computations are distributed and that too they're all doing in parallel, because there's such large numbers of computation we are doing with so many neurons and so on. It just doesn't make sense to use sequential hardware, and of course you have GPUs and so on, right? General purpose graphical processing unit and so on. So anyway, I leave it to the distributed processing people to answer those kinds of questions. And I would say, yeah, I agree. We need to do distributed computing to do this type of computing. Okay, so mine is not a very detailed answer to you, but that's how much I know about it. Okay.
So the next question is, can you brief about the security aspects of deep learning?
Security aspects of what kind of deep learning?
They've typed it as iDeep.
iDeep. Okay. I'm not sure what you mean by I is like how Apple says I, right? Yeah. Well, I'm not. I don't know what you mean by deep learning. I haven't come across that. And security aspects, what are the applications? Or yeah, of course, there are issues. One can say, look, in supervised learning, you need lots of data. You're learning from data about people, and can you maintain the security of all that information? You don't want to be revealing as to whose medical records you're using, and what are the applications or learning the data? Yeah, there are, of course, there are issues. One can say, look, in supervised learning, you need lots of data. You're learning from data about people, and can you maintain the security of all that information? You don't want to be revealing that type of security as to whose medical records you're using. And what are the applications? One is about the inherent technology. The other one is the applications of the technology, which is what are the kinds of problems you can apply in security, such as intrusion detection. That's just a simple machine learning problem where you have supervised learning, unsupervised learning, to say that particular sequence of actions is an intrusion, and we've detected that. So that would be just yet another application. Deep learning can be applied to anything really. So so security is just another application. But is there a security issue within a deep learning program? Is an interesting deep learning question, and that has to do with dealing with managing the data and so on. There are some very interesting solutions I've seen on how to maintain data security while doing the processing. Okay, yeah.
The next question is, how good is the analogy between single neuron and an activation function, as neuroscience itself is not able to find how single neuron works?
Okay, all right, good. I'm glad I'm getting these perceptive questions here. Well, McCulloch and Pitts were doing their work in 1942. I think their paper is 1942. They're the ones who first came across this idea of a formalized neuron and said, a bunch of inputs, and you weight them all, add them up, and then it fires, and then we can do it with a sigmoid function. So that is an idealized neuron. Of course, that idealized neuron has gone through various iterations. We replaced the sigmoid with hyperbolic tangent function, and then we now have the ReLU function, which is no longer sigmoid, which is no longer continuous. It's kind of a piecewise linear function and so on. So it has gone off into less and less biological looking. ReLU looks less biological than the original sigmoid, and ReLU has numerous advantages that it performs so much better. And why does it perform better? Is well, it attacks the vanishing gradient problem. When you have a network with layers upon layers and you're trying to compute gradients, they become so small when you're doing your chain rule of calculus and so on. You're multiplying small numbers with small numbers, and there's all zeros. So it is useless to do any learning. So ReLU seems to perform well. So we might be losing some of that neurobiological analogy when we have gone off in that direction. But that's what's being used largely today. So it's less biological and more simple computational. But anyway, we started out there and then we go off in these pathways. So maybe we need to be back there. If we say, well, we aren't doing as well as the human brain, where did we go wrong? Says, okay, go back from ReLU to something more biological. This is why this is exciting. This all started in 1942. Neural network type of research. And perceptron was built in Buffalo, which is near where I live normally. When it's not COVID, I'm in Bangalore. Yeah, so perceptron was built in the 1950s, that's like 70 years ago. And still we haven't perfected all of this. It's going on and on and on. But rapidly progressing, people are discovering things. But it always pays off to look at the analogy of the human brain. Because human brain is also distributed computing. It also involves these kinds of neuronal type of cells and wake dream phases, and there are so many different things that we can draw inspiration from. So it is not exact one-to-one. So yeah, we are not claiming these neurons are exactly one-to-one to biology.
So I think it was Selvi madam is asking a question: in which application capsule networks are preferred over CNN?
Oh, all right, Selvi. Selvi is head of the department at telecommunications at MS Ramaya. Pleasure to know her. And Selvi, I don't know. I don't have a good paper. Actually, when capsule networks paper, the first one that Hinton wrote was only about 2.5 years ago. And it was made available on the web before even it got published. And so I was teaching it in my class when the paper is not published. Everybody was working on next version of capsule networks even before it's published, because it was in the archives and so on. And so by the time the paper came out and they were going to present it in a conference, they had to talk about all the future improvements others have made after this paper was made available. So that is the rate at which things moved on. And I think people have applied it to varieties of things. Other than the Picasso face, something about scenes with people and churches in it. I've seen some papers that have alluded to them, and also Geoffrey Hinton applies all his work to MNIST handwritten digits. So his original paper showed we can do pretty well on handwritten digits using capsule networks, and I don't know if they did it slightly better, but it's a problem where people have got very high accuracy, so it's hard to kind of beat that. And they were able to show that. So begin with the fruit fly of AI, which is handwritten digits, and you can do very well with capsule nets. And then try out another problem domain where you can try that out. So I would ask you to do a forward search from the early papers on capsule nets. It's not as hot now as about a year or so ago, but the whole field of neural networks is exactly like that. Something becomes hot and everybody drops it like a hot potato and then goes on to the next thing. And then the old thing becomes again the important thing to pursue. So nobody should give up on any of these things and pursue all these lines. Believe in it strongly, because the entire field of neural networks was being trashed for a while, saying, what is this stuff? Why does it have to look like the brain? Why can't we just use an if then else expert system? And then the whole field of neural networks was kind of dying off. And then everything came back again saying, oh no, this is the right way. So like that, we go through the phases. Bandwagon effect of science. Bandwagon effect means everybody's jumping on one next thing that's come around. And then everybody's doing the same thing. And then they're forgetting about the previous one. So I would encourage you to look at it and keep me posted about how well you did or how well you didn't do on capsule networks.
So we have the last question, sir. Are there any prospects on amalgamation of self-supervised learning and knowledge graphs? If there are already existent application over this, can you, sir, please shed some light on that?
All right, that's a very thoughtful question. amalgamation of self-supervised learning is just an emerging topic. It's more recent than capsule nets. It's a favorite topic of one of the 3 Turing Award winners I mentioned. Jan LeCun thinks that is the greatest thing, is self-supervised learning. And that is largely shown itself in I'm sorry, I'm getting a hello. Sorry, I can't take your call now. Okay. Yeah. Okay. So knowledge graphs is a much more stable, mature area, whereas the self-supervised learning by Jan LeCun and his group largely apply to images at this point. It could also be applied to text also, and the topic of knowledge graphs is a broader one. It's a more of a topic in information retrieval, where you are using precision recall, these kinds of things about your interconnecting concepts and so on. But there is an aspect of it to discover these connections. Maybe we can use neural networks, just like you use neural networks to do language processing. So it is just a tool. I think of neural networks as a tool for knowledge graphs. So you can construct better knowledge graphs. So Google can do a better job in presenting information to you as a search engine company. So it's kind of a very big domain type of thing. They're dealing with billions of pieces of information, and they want to do a better job, and they can use neural networks to help them as in any other case. Whereas self-supervised learning seems like a topic of its own, trying to compete. If you look at what are the main areas of machine learning, there's supervised learning, there is unsupervised learning, maybe there is reinforcement learning here. And what about semi-supervised learning? That is not very different from supervised learning. It only with certain types of data you can use that. So that is not different. But self-supervised learning seems like another competing philosophy of saying you are going to figure out what is in this data set without my telling you absolutely anything. I'm not going to even help you with a small data set that is labeled, and it figures out something like supervised learning from the data. So there is this nebulous area in between supervised learning and unsupervised learning. We're competing now, semi-supervised learning, self-supervised learning. So it's a kind of style of computing that could be useful for knowledge graphs, I suppose. It could be useful for any other application, right? So take a look. There is not a whole lot of literature yet on self-supervised learning. I just wanted to bring it to your attention. It seems like a developing area, trajectory coming up, beginning about now.
Okay, sir. We are done with the questions. So the presentation was well organized, even in such a way that even a young researcher who's thinking of choosing AI as a research area should be good in mathematics, and he should be a good logical mathematician. And also, I could understand very easily the various supervised and unsupervised model, along with the deep learning architectures relating to human intelligence, neurobiology. So thank you very much, sir. On behalf of BNM family, we thank you for accepting our invitation and delivering a wonderful speech. Thank you, sir.
Thank you so much, Sahana, and all your assistants, Niharika, who invited me. And I guess I should thank, I didn't get to know the audience, but if you took the time to listen to what I had to say, I appreciate it. You may, my lecture slides are all publicly available, so you can go to my personal website, Sahana, and all your assistants, and you have all my lecture slides. My 40 weeks of deep learning is available, and you can go through it. I think it makes it easier to read my slides, and then of course you can go to the original material, which is contained in blogs and books and so on. But I try to bring it to the lay audience. Is what I've been trying to do. So thank you all, and you all stay safe. Okay? Yeah.
Thank you, sir.
Yeah. Bye-bye. To read my slides, and then of course you can go to the original material, which is contained in blogs and books and so on. But I try to bring it to the lay audience. Is what I've been trying to do. So thank you all, and you all
Thank
stay
you,
safe.
sir.
Okay? Yeah.
Thank you, sir.
Yeah. Bye bye. To